What? So so I didn't feel like the lecture today, part on differential privacy, was up to my standards. So I've decided to kind of re-record this part of the lecture. Right. So okay, so differential privacy is kind of a formal way to call privacy, to define privacy. And so the the idea here is that you have a data set X, and you would like to release the data set, but you're not going to release it exactly because that might uncover some people's private information. So instead, you release some data structure. And so usually the data structure is just kind of some version of the data set. We'll say S, and this will be through some mechanism on X. Okay, we're going to call this process a mechanism to create the data structure S, which is released from the data set X. Okay, and the idea, and this will always be a random process. Yes, okay. And then what we'd like to do is to ask some queries, be able to ask some queries. Ask, what will you do with the data structure? You ask queries. Q on S, and you like this return an answer that's similar to if you asked a similar question on X, right? So this doesn't totally make sense yet, but ask a question: is this object in the database or not? Right? What is the value of some scalar value? So we'd like to try and understand this, and so we like to ask queries on S, and what we like these queries to almost kind of match the query on the data set X. We'd like to approximately match them, right? So we'd like that the query on S to be, basically equal to the query on X plus some noise. Okay, and we'll often bound this noise by epsilon or some function of epsilon. Epsilon would be some sort of tolerance that we allow. Okay, and I'll explain this a little bit more next on the next slide. Okay, so epsilon differential privacy. Okay, this is defined with respect to, so we consider now two data sets, okay, X1 and X2, and these should be off by a single value. They should be off by one from each other. So for instance, if they have, one way is to say that we'll think of as X, let's call these X and X prime, okay? X and X prime, and we'll say that data set X is going to be a bunch of values, X1, X2, up to Xn. And so we'll differ X prime. X prime will be the same, X1 prime equals X1, X2 prime equals X2, except for some xi is going to not be equal to x. Xi prime is not going to be equal to xi, but then everything else up to xn prime is going to be equal to xn. Okay, so I mean, xi could be the first set or the last set, but there's some value where it's different, right? There's one term is different. And in particular, we want to say that xi prime minus xi, we're going to say that the difference between these is going to be 1. Okay, so then if we this can mean two different things. So either, either that we're going to say xi is going to be a real value. And so then xi prime is going to be, say, xi plus or minus 1. So they change the real value by 1. So we're considering these data sets. Or we'll say xi is going to be in 0, 1. Okay, where if it's 1, that means it's in the data set. If it's 0, it's not in the data set. So then we would say that for any range, if we look at the range intersect x, this is going to be equal to some number k. And then we'll say that the range intersect, so this will count the number of 1 things in there, things that are 1 bits. Range intersects x prime will be some number k prime, and we'll say k minus k prime is equal to 1. Okay, so these will be 2 data sets that are going to be off by 1. Okay, on any sort of query, we ask either by what things are in there. So think of the x values binary being these are the people who have cancer and the zeros are people who don't have cancer, or they're a bunch of scalar values, and one of them is off by 1 value. Okay, so we're going to consider these 2 data sets. And then here's the equation which defines epsilon differential privacy on 2 data sets on x and x prime, such that the range intersect, or that will say that say x, the symmetric difference between x prime, or the difference between them is going to be off by exactly 1. So they're 1 thing off, either on the real values in the counts or in the binary things. Ultimately, because 0 and 1 are a difference of 1 from each other, means the same thing. Okay. So then for epsilon differential privacy to hold, we want the probability, we want a probabilistic statement that on any query, such as a range query, on the data structure S, we want to see, does this fall into some range of possible values? We want to look at the ratio of this over the query on S prime. Right? Remember, we have that S is the mechanism applied to X, and S prime is the mechanism applied to X prime. And we look at the ratio of these 2 queries, whether they fall into some range. Okay, and for this to be true, then for any query we ask, a counting query, how many things are in the set, that the probability that they're in some range, there are a lot of people with cancer or not a lot of people with cancer, should be off by e to the power epsilon. Okay, and the way to think about this is approximately 1 plus epsilon. Okay. And so does this query value fall in a range? That is, it's a little bit hard to think about. An equivalent thing is to say, can we say, does the query value, what do we looked at instead? The query value of S is equal to some value. Okay, well, we're going to deal with continuous probability. So the probability that we're going to perturb this by some continuous amount. And so the probability equals the exact value is going to be 0. But we're going to look at the ratio of these things. So it's pretty much okay to think about it this way, right? So we're going to look at the probability. So a simpler way to think about this is probably that the query value, the count of over some range, is equal to some value R. And think of this as the likelihood instead of the probability, but I'll just write the probability down for over S prime is equal to some value R. So look at the ratio of these 2 things. If it's true for every value R, then if I add them up, it'll satisfy. So if I'm going to say we can kind of think about this property instead. Okay, so if this ratio is true for every little value, little r, then it'll be true for all the little values, little r, inside this range. Think of like cumulative density function versus the probability distribution evaluated at a single point. So that's kind of the distinction here. All right, so what does this mean, right? What does this mean? What if e to the epsilon. Yeah, how do we think of this? This is approximately 1 plus epsilon, right? So let's say if this ratio probability of Q of S, I want to know if I ask a query and let's say the value is R versus Q of S prime equals R. Let's say this is equal to 2. Well, that means that the probability that my kind of the implication of this being that if each are is equally likely to each other, I'm just as likely to predict, or I'm twice as likely, so twice as likely to predict that the true data structure is S and not S prime. So I think S might be more likely, twice as likely as S prime. Okay, so that I think that xi is could be xi is equal to 1. That the ith person has cancer if this is this thing flipped. How confident can I be? If I'm twice as likely, well, okay, I've leaked some amount of information. If this ratio of S versus S prime, if this is equal to, say, something much larger, like 99, okay, then I'm saying if these are the two options, S or S prime, right, someone has cancer or not, I'm 99% sure then they have cancer, right? Then I'm 99% sure that S, that the actual data says X and not X prime. So I'm pretty confident. On the other hand, okay, if I write this down, the probability S prime is small. It's going to be something like 1.01, right? So this would correspond to approximately epsilon equals 0.01. So epsilon is like 1 over 100. Okay, so this would be a small amount of small epsilon differential privacy. Then I am not sure which of X or X prime. The probability of them is basically equal, right? If this is 1, then they're equally likely, right? But if it's slightly bounded by slightly less than 1, if it's always for any query between 1, between 1 and 0.1, then I think these things are basically equally likely, and I don't know which it is. So if epsilon is small, then I'm more private. So I've secured more information, and this is a way of formalizing this property. All right. Okay. So this kind of abstractly, if I have this property where for any query that the ratio of the probability is of whether S or S prime is equal to the value I observe, that R, let's say I observe the value R, which one is more likely? If the ratios are always close to 1, then I have a lot of privacy because I don't know which one is true. I don't know if this element is in the data set or not. Okay, so how do we achieve some mechanism like this, right? The main mechanism is called the Laplacian mechanism. Okay, how does the Laplacian mechanism work? It basically adds Laplace noise. Okay, the Laplace function, LAP of X with the parameter W, the bandwidth parameter, it looks something like this. This is X, and there's a probability distribution that looks like this, and the bandwidth parameter is approximately W. So W is how wide it is. As W is wider, it's more spread out. Right, so technically, Laplace of X, W is the probability of seeing X, and it's a continuous probability distribution, 1 over 2W of EXP to the negative X divided by W, right? So as X gets, this is 0 here, but these are the values x along the x-axis, right? So if x is some value here, then this is kind of the height of the likelihood function. It's like a Gaussian. If it was a Gaussian, I would square the x and the w, right? And then it'd be a little bit more rounder. But the Laplacian mechanism is what we use here, and we'll see mathematically why this is true. Okay, and so when I add Laplace noise, what it's saying is that the simplest way of applying this is S is going to be a set Si, where each Si equals the original value in the data set Xi plus some Laplacian noise with the bandwidth parameter at equals to 1 divided by epsilon. Okay, so as epsilon gets smaller, I add more noise. So if epsilon is 1 over 100, then I add a noise of scale 100 to the value. If I want a kind of one differential privacy, so epsilon is equal to 1, then Laplacian noise, which is the bandwidth is 1, so not so far. Okay, so this is basically how it works. So instead of a data set x, right, x equals x1, x2 up to xn, I'm going to get a data set s1, s2 up to sn, right? And so it is, I'm going down here by plus the Laplacian noise 1 over epsilon on each one of these items. Okay, so this is, I'm just adding noise to each item, and this is going to, I'm going to argue now that this is going to give me kind of this epsilon differential privacy. Okay, we'll start with 2 examples, then we'll get to a slightly more complicated example of where you can do something slightly smarter than this. Okay, so let's look at the height example. And so, for instance, let's say a person has a height of 66 inches. Okay, and so this is value x, and data set x is just going to be a single value here, right? X is going to be the height in inches. Okay, and they want to actually kind of pretend that they're taller. They want people to think x prime is going to be 67 inches. Okay, so x prime, it's going to be a single data set, x point, it's going to be 67 inches. And so I want to say, can we distinguish these 2 things? You say, well, I'm going to release a measurement of the height, but I'm going to add noise to it. Okay, so my mechanism is going to get S. It's going to be a mechanism on the value x here. And this is going to be equal to x plus some Laplacian noise with the value 1 plus epsilon. So if their height is 66 inches, well, I'm going to add noise to it. And so they're not going to actually know what the actual height is. Okay, they're going to say that if it's, 1 plus epsilon is 1 over epsilon is 5, then I'm adding an average 5 inches to the actual height value. Right, so you want to give out some mysterious numbers and say, well, if I add, I can tell you I'm going to give you my recorded height plus, or with Laplacian noise of a value 5 here. Okay, so let's look at, now we want to look at the probability that S released is equal to 70 inches, right? So this would be, instead of 5 feet 6 inches, this would be 5 feet 10 inches if it was 70. So what's the probability? Divide by the probability that S prime equals 70 inches. Okay, let's do the calculation. Let's write, this is, we know it's going to be Laplace noise, so 1 over 2w exponent of 66 minus 60 minus 70 is going to be the likelihood for the Laplace divided by w divided by 1 over 2w exponent 67 minus 70 divided by w. okay, what's going to happen is some stuff's going to cancel. This is going to cancel. This is going to cancel. And I'll be able to write this as equal to exponent. And so if I divide exponents, I'm basically subtracting them inside. So I get 1 over w. This is true for both of them. 66 minus 70 minus 67 minus 70. Okay, and this value is 4, and this value is 3, but more importantly, the difference between these values is 1, which is what I promised. I promised these data sets were off by 1, so I can write this as exponent of 1 over w times 1, right? 1 over w times 1, and remember, if I set w equals to 1 over epsilon, which is the bandwidth, then this term is going to be equal to x of 1 over epsilon, which is just epsilon times 1, which is what we promised, right? So as long as the data sets are off by 1, then for any query like this, what is the value is equal to 70 or any number I put in there, the ratio of the probabilities of from which data set it came from is going to be exactly e to the power epsilon. Okay, so this is how the math works, right? So if it was a one differential privacy, then it's, you know, one is at most twice as likely as the other, but it could go in either direction depending on the noise. It could be unbiased in one way or the other. Okay, so this is one example. Let's do another binary example here. Let's do a binary example. Okay, and now our data set x is going to again be a single value, but now x is going to be 0 or 1 here. Okay, in particular, we're going to say that x is equal to, right, so the data set is this one value, and we're going to have x prime, which is x prime is equal to 0. Okay, so there's one data set, it's a binary value in the database, and it's either there in x or it's not there in x prime. Okay, so now we want to say I want to compare the probability. Okay, then oh, and again, what I'm going to do is I'm going to release s, which is going to be a single value s, so lowercase s, where this is the value, true value x, which remember was 1, plus some Laplacian noise, 1 over epsilon. Okay, so now we want to write down some probability. So I want to know the probability that I see that probability that a query, okay, on S is going to be equal to 1, right? That I think that this thing is actually here. Okay, so the query is, if it's in the range, is it actually equal to 1? Or is it, okay, and I can look at the ratio query of S prime is equal to 1. Okay, and remember it was there, but I added noise to it. Okay, so I can write this down as after skipping the coefficient, which cancels out anyways, I have 1 minus 1, the absolute value of 1 minus 1 divided by 1 over epsilon. And that's the likelihood for Q of S equals to 1. And now I have 0 minus 1 divided by 1 over epsilon here. Right, so 1 over epsilon was my W because I use Laplacian mechanism on this. So this is the ratio of the likelihoods. And again, this is equal to x of epsilon. Okay, so times, let me write this down below here. Okay, so I can do 1 divided by 1 over epsilon times 1 minus 1, absolute value, minus 0 minus 1. Okay, and this is equal to x of epsilon, because 1 over epsilon times this difference between these two values here, which is 1. Right, so I get back e to the power epsilon. Okay, so the probability is it's 1, or you can also calculate the probability that it's greater than 1. This would describe a range. This would work just as well. Okay, but if I observe a value 1, right, then I say, what's the probability? It's the original value was 0 or 1. Again, the ratio of these probabilities is exponential in epsilon. Okay. Okay, again, simple thing with one thing in the database. Now let's look at a slightly more complicated thing where we have a binary database. Okay, so now x equals x1, x2 up to xn, and each of these xj is going to be in 0 or 1, so they're binary values, and then x prime is going to be x1 prime, x2 prime, xn prime, and for some xi is going to be not equals to xi prime, right? One is 0, the other is 1. Okay, so I flipped one of the bits, and now let's ask some query, right? And now we can say, for instance, now I'm going to consider a range, which is going to be an interval between A and B. Okay, so this would be, these values are indexed, and so that interval intersect x. Okay, so this will be all the values xa, xa plus 1, xa plus 2, up to xb. Okay, so if I think if I have a data set, they're index 1, 2, up to some value a, to some value b, up to n, right? I've got a bunch of these data. Each of these values is either 0 or 1. Okay, and so I have a query range. The query on an interval of a data structure S, right, which is going to look like this. We'll add noise with the Laplace mechanism again, is going to be the sum of the values I in the interval of xi. I'm going to add up the values xi. I'm going to count the number of ones in here. So, okay, so if I sorted a bunch of people indexed by their age, and I want to say all the people in this age range, how many people have cancer? Okay, that's what the question would be. Okay, and so if this is my data structure on x, right, so x, this would be kind of, if I think of these as things being there or not, then it's the cardinality of x intersect this range, this interval range. This is the interval. Okay, so these are the sort of questions I'm going to ask on this binary data set. We'll look at just these interval range questions. Okay, and we're going to apply a mechanism. We'll do the Laplacian mechanism, and just to review, we're going to have that S is going to apply the mechanism on X, and so this is going to be a set S1 up to Sn, and each Sj is going to be equal to the Xj value plus Laplacian noise. Okay, so by the argument before, if I ask a query that's of size 1, I look at just one thing, by the argument we had on this slide, I have epsilon differential privacy on that one thing, right? So the probability is going to be at the difference is going to be at most that, right? So I'm going to have the difference in error is going to be kind of which one is going to be more likely based on the reading is going to be most epsilon here. Okay. But I have to store this full data set S with noise on everything. So what if I ask a range query? What if I ask how about a query on S, right? So a query defined by an interval on S. Okay, so I have two options. Option one is going to be I say that the query on S is somehow defined as the size X intersect here plus Laplacian noise here. Okay, I'm going to add Laplacian noise on the answer for this query. Now for that query, I again, by the same argument before, the query, whether the count of things at X or X prime is going to be off by 1, and I'm going to get epsilon differential privacy if I do this. Okay, but the problem is then I need to store this for all possible queries, and there's polynomial n squared number of queries. I don't want to store a value for each of these queries. Okay, I might also be able to build these queries together, right? If I can ask intersection queries, they have to agree somehow. I have to make sure that if I ask two queries that intersect only on one thing, that they aren't somehow leaking some information. So option 2 is to have the query I of S is going to be the sum of I in the interval of these SIs, where each SI, which this is going to be the sum over I of each XI plus the Laplacian noise here. Okay, what happens now is I'm getting X intersect I plus the sum of these Laplacian noises. So the size of the interval basically times the Laplacian noise. Okay, so now the amount of noise I've added to this thing is not just e to the -1 in expectation, it's the number of things in the interval times that. So I'm adding a lot more noise now. I still am going to get epsilon differential privacy guarantee, but my answers are not going to be that close. So now I'm going to say that query of I on S minus query of I on the full data set, the difference here, now I can only bound this by the size of the query times the Laplacian 1/epsilon. Okay, I can actually do a little bit better. You can actually put a square root here because I'm actually adding up these noise, and on average, the error is 0. So they don't add up independently. They add up by the variance. The variances of the noise add up, but then I want kind of the standard deviation, and so it's kind of get like the square root of these terms. Okay, so this is bounded by basically square root n times kind of this this 1/epsilon, right? So it's be bounded like this with you know some constant probability. So roughly my error is going to be square root n/epsilon, which is not great. Okay, as the database size grows, my error on the queries is going to be quite large. Okay, so I don't quite want to do this. So there's something smarter I can do instead. Okay, what can I do instead? I can have my database. Okay. Okay, what I'm going to do is I'm going to build a binary tree on this database. Okay, so for each of the cells, I'm going to build okay, I'm going to build a node for each of these subtrees. Okay, so if I look at this subtree here, there's a node here. It corresponds with this interval. Okay, so if I asked a query, so if I call this node J, and I call this interval J. So if I asked a query at interval J, then I'm going to pre-store X intersect interval J plus some Laplacian noise. Okay, that'll be true for every node in the tree, including these individual nodes here. So this is x1, and I'm going to store s1 plus some Laplacian noise as well. So I'm going to store for all the leaf nodes and all these trees. So the total number of these things is actually linear, because the number of nodes in a binary tree is linear in it. Okay, it's actually 2n minus 1, right? Okay, so I'm storing each of these things. And what you can argue is that if I make any interval in this tree, okay, any interval in this tree, I can compose it as a combination of a number of these subtree intervals, right? So I'm going to get, let's highlight them here. I'm going to get, and this individual node, right? So this is for this large query here. I can compose as a set, a disjoint set of these intervals. Okay, so I'm going to say for any I can write this as the disjoint union over the set of these intervals j, which correspond with the subtrees. Okay, and I can know that the size of j is going to be at most 2 times log n. There's basically, you look at the left endpoint, the right endpoint, and walking up the tree, and there's walking up to a common root. There's going to be at most log n 1 from each level of the tree. There are most log n levels of the tree. So this is at most log n. Okay, so now I can compose a query, right? So a query of S. Again, this is a data structure, so I can store this other information. It's now going to be the sum of these j in this set j of these subtrees of the query on the interval j of S, right? Which is going to be stored, is going to be sum j and j of the x intersect ij plus some Laplacian noise, 1 over epsilon. And so this will be equal to x intersect I, the full interval, plus now j of these, Laplacian 1 over epsilon. Okay, and because they're independent, I can add them up and put this under a square root. So this is really going to be, so if I do this properly, the query on x minus the query on s, right? The difference is going to be square root of log n, maybe there's a factor 2 in front here, divided by epsilon. Okay, so that's the expected, or times no, divided by epsilon, times 1 over epsilon noise. So that's how much noise I have. So if I want a lot of privacy, epsilon to be really small, I'm going to have more noise in my answer. If I want my answers to be very accurate, I'm going to lose some privacy because I have to make the amount of noise I add to everything very small, and then I can kind of separate them this way. Okay, so this is a little bit better insight into how differential privacy works. It's basically adding noise into the data release through some mechanism. So I'm having this Laplacian mechanism often where I'm taking the data set and I'm adding noise to things. If I add noise to a couple of extra things in a careful way, I don't really blow up the space of my data structure, but I can answer queries with much less noise on them, but still having the same amount of differential privacy. Be a little bit when I add noise in this binary tree that I can combine queries to get a better estimate on individual things. I have to be a little bit careful about this. So the error is not quite as good as I did here, but conceptually, this is kind of how it works. Okay, so we'll stop here for the extra